In the previous section, we described the differences between a LabVIEW FPGA system and an NI DAC MX system. By the end of this module, you'll be able to describe the LabVIEW FPGA architecture on Windows and LabVIEW FPGA architecture with LabVIEW Real-Time. In Lesson 2, getting started with LabVIEW FPGA, we'll start off by talking about evaluating system requirements. Then we'll talk about how you configure your system, and then finally we'll create a LabVIEW FPGA project. Here we see what the FPGA development flow looks like. So in Lesson 2, we'll talk about evaluating your system requirements first, and then you select the appropriate architecture. Next, you configure your hardware, and you create a LabVIEW project. So here we are evaluating our system requirements. So this is an overview slide, and we'll talk about more on each of these in the coming slides. So first of all, you need to determine, do you need FPGA? Do you need the reconfigurability and the speeds that are offered by FPGA? If yes, then the next thing you need to do is to select the RIO architecture. So you can either do a FPGA for Windows or FPGA for real-time. Once you've selected that, then you have to figure out what's the platform that I want to run on. So do I want to use a PCI or PXI, or am I going to use a CompactRIO? So after you've selected your platform, then you might want to think about other considerations when you're selecting your hardware. For example, you might want to look at the FPGA size, what kind of I/O do you need, and things like that. In this course, the exercises will be done on two different platforms. So one will be for FPGA for Windows. You'll be using a PCI R-Series card. And if you're doing the real-time exercises, then we'll be using the CompactRIO platform. In this slide, we see two FPGA system architectures. One is LabVIEW FPGA architecture on Windows, and another is LabVIEW FPGA architecture with LabVIEW Real-Time. In the next slides, we'll dive more into this. For now, I just want to talk about the differences between whether you'd want to use something on Windows or if you would want to move to something on real-time. The benefits of running something on a real-time operating system is that it's going to be more reliable, and also it's going to be more deterministic, which means it's going to have less jitter. And you're going to be able to more reliably predict how fast it's going to take something to run each given time. For more information about real-time, you can go to ni.com/realtime, or you can take the LabVIEW Real-Time course. So here we see what the FPGA with Windows looks like. So if we're taking a look at the slide, you see that first of all you have a computer that's running the Windows operating system. So this could either be a PC or it could be a PXI system, but regardless, it's running a Windows OS. So notice that you've got your FPGA inside the system. So you might have a PXI or PCI FPGA board that's inside your computer. And this has an FPGA on it, and this is where your FPGA VI logic is going to run on. So notice that there's a communication piece as well. So the FPGA VI is going to be able to communicate with a host VI that is running on your Windows computer. Here we see what an FPGA with real-time system looks like. So if we look on the right, you'll see that there is a LabVIEW Real-Time system, okay? And the LabVIEW Real-Time system is running a real-time operating system. So this piece of hardware could either be a C-RIO, a single-board RIO. It could also be a R-Series that's running in a PXI chassis that is running real-time OS. So if we take a look at that, again, we have an FPGA piece, and this is the FPGA hardware. Again, this is going to be running the logic that's defined in our FPGA VI. That FPGA VI is going to be able to communicate over the bus to a host VI that is running on your real-time operating system. And then another piece we have here is the Windows system. So if you want a user interface for your application, then you'll be developing a VI on a Windows machine, and that Windows VI is going to be communicating with your real-time operating system through network communication. So here we see LabVIEW programming in CompactRIO. So let's take what we just talked about in that last slide, where we have a LabVIEW FPGA system running with real-time, and let's see how that maps out to our hardware. So first, let's start with the FPGA. So if we look on the right, we see a CompactRIO hardware, and we see some I/O modules. So behind the I/O modules, it's connected to a backplane of that CompactRIO, and on that backplane, that is where the FPGA exists. So the FPGA is going to be able to communicate with our real-time operating system. So in the case of CompactRIO, the real-time operating system is executing on the CompactRIO controller. So the other piece with Windows, you notice that we've got a laptop on the left. And on the laptop, we've got a Windows operating system running, and we have a VI that's running on Windows. And this is going to provide our user interface. This Windows VI is able to communicate with our real-time processor through the network. Now you can describe the LabVIEW FPGA architecture on Windows and LabVIEW FPGA architecture with LabVIEW Real-Time. Next, we will describe common reconfigurable I/O platforms. In the previous section, we described the LabVIEW FPGA architecture on Windows and LabVIEW FPGA architecture with LabVIEW Real-Time. By the end of this module, you will be able to describe common reconfigurable I/O platforms. Here we see common reconfigurable I/O platforms. So one is PCI and PCI Express if you want to put an FPGA board into a computer with PCI slots. Also, there's PXI and PXI Express if you want to put an FPGA board into a PXI system. And also there is CompactRIO. Here we see the R-Series multifunction RIO board. So this board comes in a PCI, PCI Express, PXI, or PXI Express form factor. You can use this to define custom data acquisition, and it's a multifunction board, so it has analog inputs, analog outputs, and also digital I/O. Also, it has a high channel count. Here we see a CompactRIO system. So first thing you can select is the reconfigurable chassis. So this chassis is going to be the component that contains the FPGA, and then you can also select the real-time controller. This is going to be where your real-time OS runs, and depending on what kind of controller you want, you can select the processor speed and flash memory size. Also, you want to select the I/O and connectivity. So if we look back on this graphic, you see how there's different modules in there, and each module you would select based on the I/O that you need, whether you need temperature, whether you need digital I/O, whether you need analog input, and things like that. Here we see some other CompactRIO form factors. So the one on top, we see an NI CompactRIO integrated controller. In this case, the controller is connected automatically to the FPGA. So the FPGA and controller are one piece. Another thing we see here is a NI Single-Board RIO. In this case, this is essentially the same thing as a CompactRIO, except it doesn't have the enclosure, and you can get it in a board format. Here we discuss FPGA size. So historically, FPGA size was measured by gate count. So here you would just say, well, whichever FPGA has the bigger gate count, that's the one with more resources and that has higher performance. However, now FPGA logic blocks and resources differ, so logic capacity and performance comparisons are tricky. So for example, now FPGAs might have specialized blocks. So some might have more multipliers, some might have more block RAM and things like that. So it's not a straight comparison anymore. Also, the logic blocks might differ in capabilities. So one FPGA might use 4 input lookup tables, and the other one actually uses 6 input lookup tables, which can do more. So it's difficult to kind of just look at one spec and look at the gate count, and having that determine how powerful an FPGA is. Another thing is, it's difficult to map LabVIEW VIs into FPGA resources. So it's difficult to just look at your LabVIEW FPGA VI block diagram and know exactly how many resources it's going to need on the FPGA. What happens is the Xilinx compiler actually takes a look at the converted LabVIEW code, and it optimizes code based on the FPGA architecture. It maps things out to specific FPGAs. One thing you can do is you can verify that your FPGA code fits by compiling for offline hardware targets. So for example, if you don't have your FPGA hardware quite yet, in LabVIEW FPGA you can simulate that hardware and then try to compile your FPGA VI to see if it's going to fit. Another thing you can do is, instead of waiting for something to compile, you can also do a resource estimation, and we'll talk about that in a later lesson. So here we see an FPGA resource table. So because it's difficult just to compare the gates, what we have in this table is you see there is a row for equivalent logic cells. So here we try to kind of give a good comparison on the equivalent number of logic cells for each of those FPGA chips. So if you look at that top row, those are different example Xilinx FPGA chips. So here we see on this particular slide that the Vertex 5 LX110 has the most equivalent logic cells. Also, we see the number of resources for different things on that FPGA chip. So if you look on the left, You also see the number of lookup tables or flip-flops. You also see the number of multipliers on each FPGA chip, also the amount of block RAM, and in the last column you see sample NI products. So each of those NI products, it's mapping out which NI products use which Xilinx FPGA chips. So this is a lot of information. If you want more details on this, refer to the link that is shown on this slide for more information. So at this point, if you're able to, it would be helpful to do exercise 2.1. In exercise 2.1, you set up your CompactRIO system, and you're able to connect and power it up, and you can verify the proper connections. So if you have the hardware that's necessary to do this exercise, go ahead and do it now. So in this slide, we have a few discussion questions. So if you need to swap modules, do you first need to power off the CompactRIO system? With CompactRIO, the modules are hot swappable. So even if the CompactRIO system is on, you can feel free to take out modules and swap them while the CompactRIO is on, and that'll be no problem. The next question is, both the FPGA and user 1 LEDs are user configurable. So if you look at your CompactRIO, there's a couple of LEDs that are on that controller. So you'll see one labeled FPGA, and you'll see another LED labeled user 1. So what are the differences between these two? So the FPGA LED, that is an LED that you can control in your FPGA VI. The user 1 LED, that one is not accessible by your FPGA. Instead, you would access your user 1 LED through the real-time VI. Now you can describe common RIO platforms. Next, we will configure a Windows FPGA system. In the previous section, we described common RIO platforms. By the end of this module, you will be able to configure a Windows FPGA system. Okay, so how do you configure your system? So before you install any of your devices, what you want to do is install the right software on your development computer. So the first thing you want to do is install LabVIEW. If you happen to be using a real-time controller, then install LabVIEW Real-Time. After that, install LabVIEW FPGA. And then lastly, install the NI-RIO driver or other target-specific software. After you're done installing everything, then go ahead and connect up your hardware. Once you've configured a Windows FPGA system, if you're using a R-Series board, for example, go ahead and open up the Measurement and Automation Explorer, otherwise known as MAX. And if you open it up, you should see your R-Series board show up under Devices and Interfaces, as you see on this slide. Now you can configure a Windows FPGA system. Next, we will select the host target network setup for a real-time FPGA system. In the previous section, we configured a Windows FPGA system. By the end of this module, you will be able to select the host target network setup for a real-time FPGA system. Here we see some high-level steps for configuring a real-time FPGA system. So the first thing we'll talk about is selecting a host target network setup, and then detecting the remote target. Then we'll configure the target network settings. We'll view devices and interfaces, and lastly, we'll add and remove software. So this module will focus on that first piece right there. Okay, let's talk about the host target network setup. So let's talk about two different options. Okay, so option number one is you have your host computer and your real-time target connected to the same local area network. So in this case, they're both connected to your local area network, or LAN, and typically a LAN will have a DHCP server. So we'll talk about what DHCP is in some of the coming slides. The other option is you have your host computer and your real-time target connected directly to each other using a crossover cable. So in this case, you have a real-time target, and then you've got a crossover cable connected on one end there, and the other end of that crossover cable is connected to an Ethernet port on your host computer. Okay, so that's the direct connection setup. So regardless of which setup you use, both the host computer and the target need an IP address. Okay, we'll talk about what an IP address is in the next slide. To configure a remote system, the host and target need to be on the same subnet. So to do this, sometimes you might need to temporarily disable your firewall. Okay, so now let's talk about what an IP address is. So an IP address is the unique address of a device. So for every device that's connected to a network, there's going to be an IP address associated with it. Okay, so an IP address is a set of 4 1 to 3 digit numbers in the range of 0 to 255, and you'll have this dotted decimal notation. So if we look at this example IP address, it could look something like this. It could be 224.102.13.24. So that could be an example IP address of your real-time target, for instance. The next thing we'll talk about is a subnet mask. So a subnet mask is a code that helps a network device determine whether another device is on the same network. Okay, so let's go through an example to explain this. So the most common, or one of the most common subnet masks is 255.255.255.0. So if this is your subnet mask, then for two different IP addresses to be on the same subnet, then the first 3 numbers need to match. Okay, so for example, let's take a look at our example IP address. So if we had a real-time target with an IP address of 224.102.13.24, an example of a host computer that would be on the same subnet, it would have to have an IP address that starts with 224.102.13. And that fourth number could be anything between 0 and 255. Okay, so the IP address is a unique address of your device, and your subnet masks tells you if another device is on the same subnet. The last 2 bullets we have here are gateway and DNS address. These have the word optional next to them because a lot of times you don't need to configure these. The reason why is if you have your IP address and subnet mask, once you submit those, the gateway and the DNS address can be automatically generated. In this slide, we see a couple different options for IP addressing. So let's talk about the first one. So the first one we see here is DHCP. Okay, so if you have a network and it has a DHCP server, what that does is each time you connect a device to that network, the DHCP server will automatically assign an IP to each device that connects to that network. So for example, if I had a local area network and it has a DHCP server, if I had a real-time target and I connected it up to the network, the DHCP would automatically assign that real-time target an IP address. And if I connected up my host computer to that same local area network that has a DHCP server, then the DHCP server will automatically assign my host computer a different IP address. So this is a common network protocol for administering IP addresses. The next one I want to talk about is link local. So link local addresses are network addresses intended for use in a local area network only. So if you have a link local address, it's always going to have 169.254.some number.another number. So the auto IP feature, what it'll do is when you connect something up to the network, it'll first try to see if there's a DHCP server. And if there is no DHCP server, then it'll automatically try to use a link local address. So let's say I have a real-time target with auto IP. Well, when I connect that up to a network, the first thing it's going to do is it's going to look, hey, is there a DHCP server out there that's going to assign me an address? And if it looks for that and it doesn't find a DHCP server, then it'll automatically default to a link local address instead. So what that means is if it doesn't find a DHCP server, then it's automatically going to assign itself an IP of 169.254.some number. The last option I want to talk about is static IP. So a static IP is just an IP that's not going to change that you can manually assign your device. So for example, if I connect up a real-time target and I want to assign it a static IP address, then I'm going to manually say I want the IP address to be something. So for example, I can say I want to assign a real-time target in a static IP address of 10.0.0.4. And that way I'm manually assigning the IP address instead of allowing something else to assign it for me. Okay, let's talk about these IP addressing options with a Windows host and how they also work with a real-time controller. So first, let's talk about a Windows host. On a typical computer running Windows, what it'll do is it'll first look for DHCP. So if you connect up that computer to a network, it's going to try to see if there's a DHCP server to assign it an IP. And if it doesn't find one, then the Windows computer will default to using a link local IP address. So remember, a link local IP address will be 169.254.something.something. However, you can also assign a Windows computer a static IP, and this is something that you can configure in the Windows environment. Now let's talk about IP addressing options with a real-time controller. So if you're using a real-time controller, usually by default it'll look for a DHCP server when you first connect it to a network. And again, if the real-time controller has a auto IP feature, what it'll do is it'll look for the DHCP server first, and if it doesn't find one, then it'll use a link local address instead, which is again 169.254.something.something. You can also assign a real-time controller a static IP if you prefer instead. And the way that you would assign a static IP address to a real-time controller is you would open up Max, or the Measurement and Automation Explorer, and you would manually assign the static IP address there. Now let's talk about Ethernet cabling options. So let's talk about the use case where your host computer and your real-time target are both connected to a hub, router, or network switch. If this is what you're doing, then the type of cable you want to use is a standard Ethernet cable. So these are typically cables that look blue. Now let's say you are using the setup where you're connecting your host computer directly to your real-time target. In this case, you would want to use a crossover Ethernet cable. And the difference between a standard Ethernet cable and a crossover Ethernet cable is pretty similar, except with the standard Ethernet cable, the wiring goes straight through, and then on a crossover cable, two of those wires are flipped. These days, most of the times, you don't have to worry about which type of Ethernet cable you're using. Most of the times, devices are able to figure out what type of cable it is and automatically adjust for it. Now you can select the host target network setup for a real-time FPGA system. Next, we will detect the RT target and configure the network for a real-time FPGA system in the Measurement and Automation Explorer. In the previous section, we selected the host target network setup for a real-time FPGA system. By the end of this module, you will be able to detect the RT target and configure the network for a real-time FPGA system in the Measurement and Automation Explorer. So our next step after selecting the host target network setup is to detect the remote target in MAX, or the Measurement Automation Explorer. From now on, I'll just be referring to the Measurement Automation Explorer as MAX. Okay, let's walk through the steps of detecting a remote target, in this case a CompactRIO. So the first thing we would do is we'll connect our CompactRIO to a host PC through a network. Then we'll power up the CompactRIO. If the CompactRIO is not configured, its status light will blink slowly to indicate that. The next thing we'll do is we'll open up MAX, and then we'll take a look at the remote systems in MAX, which shows the devices that are connected over Ethernet. Here we see a screenshot of MAX. So notice to detect the RT target, what we'll do is we'll go to the remote systems and we'll expand it. Under remote systems, this is where our RT target will appear. So let's take a look at what that looks like in MAX. So here you can see on my host computer, I have opened up MAX, and I also have a CompactRIO connected to the same network. So what I'll need to do to detect it is I'm just going to go over here to Remote Systems, and what I'm going to do is go over here and expand it. So let me click that. And once I've done that, MAX is now searching for some remote systems, and notice that it has found my CRIO over here, and I can select my CRIO now that it's been detected and take a look at some of the settings. Now that we've detected our remote target, the next thing we need to do is configure the target network settings. The recommended approach to configuring the network settings is to attempt to obtain an IP address automatically. So this will work if you're connected, if the RT target is connected to a network with a DHCP server, or if the controller supports the auto IP feature. So for example, if we set the RT target to obtain an IP address automatically, and we connect it up to a local area network, first it'll look and see if there's a DHCP server. If there is one, then it'll automatically get assigned an IP address. If there is not a DHCP server, then it'll automatically default to a link local address. However, if this recommended approach doesn't work, then you can also try to specify the IP address manually by using a static IP address. Here we see in Macs how you would automatically obtain an IP address for your RT target. First thing you would do is in Macs, you would go to Remote Systems and select your RT target. And then on the section to the right, you would go ahead and select the Network Settings tab. Once you've selected the Network Settings tab, you'll be able to configure a couple things. What I want you to see right now is over here, there's this item called Configure IPv4 Address, and you want to set that to DHCP or link local. Once you've done this, then click on Save, and once you've clicked the Save button, you've configured your RT target to automatically try to obtain an IP address, either from the DHCP server, and if it doesn't find one, it'll default to a link local address. If instead you would like to manually specify an IP address and use a static IP, this is how you would do it in Macs. So in Macs, again, you would go to the Network Settings tab of your RT target, and then this time on the Configure IPv4 Address item, you'd want to select static instead. Once you've selected static, you'll be able to manually configure what the IP address is going to be. In this case, we see that we have used the IP address of 10.0.5.2, and we've also manually specified the subnet mask 255.255.255.128. Once you've manually specified your IP address, then go ahead and click on the Save button, and it'll save those settings to your RT target. Now let's take a look at what this looks like in Macs. Okay, so now we're in Macs, and notice that over here, under the Remote Systems, we've already detected our real-time target. In this case, it's the CompactRIO 9074. And once we've selected it, we see that we have a General Settings tab under our System Settings tab. So under General Settings, we see what the host name is. We also see the IP address. So now, after we've detected it, we know that we need to go to the Network Settings and configure those. So I'm going to hover over here, and I'm going to click on Network Settings. And notice right now this RT target is using a DHCP or link local address. So this is set to automatically try to find the IP address. Okay. So notice that there happens to be a DHCP server on this network, and the DHCP server has automatically assigned my real-time target an IP address of 192.164.2.143, and also a subnet mask. Now let's say I wanted to select a static IP address instead. Well, to do that, I would select this item right here and change it to static. So if I choose static, notice that now I can manually specify it and give it a static IP address. So instead of using this IP address, I could assign it a static IP address with 150. And I can also change the subnet mask manually if I want as well. And if I wanted to keep those settings, I would just have to go over here and click on the Save button to save it. So now you know how to configure the network settings in Macs for your real-time target. Now you can detect the RT target and configure the network for a real-time FPGA system in Macs. Next, we will add software on the RT target in Macs. In the previous section, we detected the RT target and configured the network for a real-time FPGA system in Macs. By the end of this module, you will be able to add software on the RT target in Macs. Okay, so after you've configured your target network settings, the next thing you want to do is view devices and interfaces in Macs. So here we have a screenshot of Macs, and over here under our real-time target, in this case it's a CompactRIO, we can expand devices and interfaces and make sure everything shows up correctly. So in this case with CompactRIO, we just want to make sure that we see that FPGA appear correctly, which we see here as RIO 0. If you're using a PXI chassis that's running a real-time OS, then you'll want to make sure that the devices and interfaces show up accordingly and show the right boards in your PXI system. The next thing you want to do is add and remove software accordingly on your RT target. So here we have another screenshot of Macs, and notice under your RT target there is a tab called Software. So what you want to do is you want to select that software and then click the Add Remove Software button, and that'll launch a wizard that allows you to install software onto your RT target. Here we see one of the screenshots of the Add Remove Software wizard. So here you can see that you can install software add-ons. You can also use the wizard to install a recommended software set. So let's take a look at that in Max now. So here we are back in Max, and we're going to go to our remote systems. We see that our RT target is right here. I'm going to go ahead and expand it. And what we want to do now is we want to install software onto our CRIO. So I'm going to click on Software, and next thing I'm going to do is click on Add Remove Software. So now I see a wizard where I can install software onto my CRIO. And notice here I've got NIRIO 12.1. And I can go ahead and select this and click Next to install the recommended software set. So notice that we've got a recommended software set over here. We also have a bunch of add-ons that we can install as well, and we've got a list over here. So I'm going to click Next. On this screen, we can see and select which add-ons we want. So notice that there's a lot of them. There's, for example, PID and Fuzzy Logic Toolkit. There's Network, I/O, Scan Engine, and things like that. So for now, I'm just going to click on this button, and that selects all of them. So if you want to be safe, you can install all of them just to make sure you have everything. And later on, when you know more about your application, you can go ahead and come back here and deselect the ones that you don't need. After that, select Next. And on the screen, we see which ones we want to install. And then if you click Next, that'll actually begin the update, and it'll start installing the software onto your RT target. And this is what you would do. These are the steps that you would take to install software onto your RT target. Okay, at this point, if you're able to and you have the hardware, go ahead and do exercise 2.2. And in this exercise, you'll configure a CompactRIO system. So you'll open up Max and you'll be able to configure the network settings, you'll add software to it, and things like that. In the previous section, we added software on an RT target in Max. By the end of this module, you will be able to create a LabVIEW FPGA project for an FPGA target in a Windows computer. In this slide, we see an overview of the steps that are required for creating a LabVIEW FPGA project. So the first thing you want to do is in LabVIEW, you want to create a new project. Next, you want to add a target. So this target, if your device is local, so if you have an R series FPGA card and it's inside your computer, then you would want to add the target under the My Computer item. If your device is networked, for example, if you have a CompactRIO that's attached to the same network as your computer, then you would want to add that target under the project item. The next thing you'll do is number 3, you'll discover the existing device or create a new device. So if you have an online device, so if you have a device that's actually already installed or attached to the same network, LabVIEW can go ahead and discover the module and I/O nodes. If you have an offline device, for example, if you're creating a project for a FPGA target that you don't currently have in your hands, what you can do is you can create an offline device and add the modules and I/O nodes manually yourself. If the device is a network device, make sure you connect the target to the network. In this slide, we talk about how to create a new FPGA target if it's on a FPGA for Windows system. So the first thing you want to do is you want to right-click My Computer and then select New and then go to Targets and Devices. So this is what you would do, for example, if you had a PCI R series card inside a Windows computer. This will launch a new window that says Add Targets and Devices on My Computer. So notice there are 2 different options at the top. So one option is Existing Target or Device. So if you have your R series card and it's already installed inside your Windows computer, you can go ahead and select Existing Target or Device and then click OK. And then what that'll do is it'll automatically detect that target and add it for you. However, if you do not currently have a FPGA board that's installed on your computer, you can go ahead and create one and simulate one by putting New Target or Device. So if you select that option, then notice on the slide it shows that you can select which device you want. So in this case, we're selecting an R series board, and in particular a PCI 7831R. So once you select that and click OK, it'll go ahead and create that simulated device. So here we see how the LabVIEW FPGA project is kind of associated with the graphics that we showed before in this class. So notice that on the FPGA project you have that My Computer item. Well, that My Computer item represents your Windows computer. And then underneath it, notice that as part of the My Computer, there is a FPGA item under there. So that FPGA target, that represents the FPGA board that is inside your Windows computer. So now let's take a look at how we do this in LabVIEW. Okay, in this demo, I'm going to be going through the high-level overview of the steps in exercise 2.3, where we create a LabVIEW FPGA project for an R series device. Okay, so let's say you're doing a LabVIEW FPGA project, and you know you're supposed to be doing it with a PCIe 7852R R series board. However, you don't have that in the mail yet, and you want to get started on it though. So in this case, what we can do is we can create a LabVIEW FPGA project, and we can go ahead and create an offline R series board, so we can start working on it before we actually get our hands on the device. So the first thing we're going to do is we're going to go to Create Project, and then we're going to select Blank Project. And now we've got a blank project here. Okay, so the first thing we're going to do is we want to create an offline R series board. So we're going to right-click My Computer. We're going to go to New, and then we're going to go to Targets and Devices. So instead of choosing Existing, since we don't actually have the R series board yet, we're going to go to New, Target, or Device. Then here we're going to go and browse for it. So I know it's an R series board, and I know I want a PCIe 7852R board. So I'm going to select that and click OK. So now you can see that I successfully created a 7852R board, and our FPGA target is on here, and it looks like we're ready to go. In the previous section, we created a LabVIEW FPGA project for a FPGA target in a Windows computer. By the end of this module, you'll be able to create a LabVIEW FPGA project for an FPGA target in an RT target. Okay, now let's go through the steps for setting up a project for an RT target. So if you have an RT target, what you want to do is you want to right-click on the project item. So notice it's the project item at the top there. So you would right-click that, and then go to New, and then Targets and Devices. In this window, you have two options. So you can either, if you have a RT target that's already connected on the same network, then you can go ahead and select Existing Target or Device and discover it. And then you'll be able to click OK, and the project will automatically discover your target. However, if you're trying to add a RT target and you don't have it connected yet on the network, you can go ahead and select New Target or Device. And then once you've selected that, under New Target or Device, you'll be able to browse and create the target that you're going to receive in the future. If you're using a CompactRIO, the next screen that you're going to see is a Select Programming Mode screen. So for the purposes of this course, since we are going to be using the FPGA on the CompactRIO, we want to select the LabVIEW FPGA interface item, and then click Continue. Here we see a LabVIEW project with the CRIO connected. So if you take a look at it, under your project window, you see a CRIO 9074 item, and notice that there is a bright green circle next to it. If that circle is bright green, then that's going to indicate that your CRIO target is connected to your project. If the CRIO is not connected to the network, then you'll see that green dot go to a dark green. Okay, so if you see a dark green dot, that indicates that your CRIO is not currently connected to your project and it's not connected to the network. So we see the CRIO 9074 item on the project, and that's going to represent your CRIO RT target. Beneath it, within it, there is a chassis item as well, and the chassis is what actually contains the FPGA. So this is why the FPGA target item exists under the chassis. And then finally, under that, you'll see the different modules that are connected to that FPGA. On this slide, we see how the different items on your Project Explorer are connected with the graphic that we showed earlier. So notice that we've got the My Computer item, and that's going to represent your Windows system. And then you've got the CRIO 9074 item, that's going to represent your RT system. And then within that RT system, you see that FPGA target, and that's what's going to represent the FPGA that's on the back plane of your CRIO. So in exercise 2.3, we demoed this earlier when we created a LabVIEW FPGA project for Windows. And exercise 2.4 is going to walk through instructions on how to create a LabVIEW FPGA project for an online CompactRIO RT target. So in the following demo, I'm going to walk through the steps of exercise 2.4, and feel free to follow along, and also feel free to do it on your own later on as well. In this demo, I'm going to go through some of the instructions on exercise 2.4, and we're going to create a LabVIEW FPGA project for a CompactRIO. So in this case, we have a CompactRIO real-time target, and it happens to be connected to our network already. So let's go ahead and create a project for it. So first thing we're going to do is create project, and then we're going to create a blank project. Okay, because my real-time target in this case is not on my computer, it's actually a separate CompactRIO that is on the network. I'm going to go to Project, I'm going to right-click Project, go to New, and go to Targets and Devices. And I'm going to choose Existing Target or Device since it's already connected to my network. Now I know it's a CompactRIO, so I'm going to go down here to CompactRIO and expand this. So now it was successfully able to detect my CompactRIO target that's already connected. And I'm going to select that and click OK. So in this case, I'm going to use my CompactRIO, and I want to leverage the FPGA on it. So because I want to use the FPGA, I'm going to select FPGA Interface and click Continue. In this case, I do want to discover what C-Series modules are connected to it. So I'm going to click Discover. And now if you look at the project, notice that it was able to detect my CompactRIO. Notice also that we have a bright green dot over here. This means my project is connected to that CRIO right now. Notice that it discovered the chassis, and then under the FPGA target, we've got different types of I/O. So we have chassis I/O, we have I/O from one of the modules. So here we have thermocouple 0, 1, 2, and 3. We also have analog input here for this module. We also have analog output. And here we have the different modules here. So I'm going to go up here. And you can also collapse these down if you don't need to see them at the moment. And now we've successfully added a CompactRIO target to our LabVIEW project. In the previous section, we created a LabVIEW FPGA project for an FPGA target in a real-time target. By the end of this module, you will be able to use the LabVIEW FPGA project template to create a LabVIEW FPGA project. So in this demo, instead of creating a FPGA target in your project from a blank project, we're going to use something called the LabVIEW FPGA template. So let's go to Create Project. And then I'm going to go to Templates here. And then here there's a template for the LabVIEW FPGA project. Okay, so this one is another way of creating a project with a FPGA target. So I'm going to double click this. And notice if I go with this method, there's a wizard that kind of walks me through creating a project. So notice you can choose different ones here. In this case, I'm going to go ahead and choose the CompactRIO Reconfigurable Embedded System. I'm going to click Next. And in this case, let's just say we don't have the system currently connected. I'm going to choose Create New System. Click Next, and it's going to walk me through some other things. So notice that we've got a wizard that says, okay, well, what kind of controller do you have? In this case, I have a CRIO 9074, so I'm going to select this one. I'll click Next. And then the wizard's going to ask me, okay, well, what modules do you have on it? So let's say I have a 9211 in slot 1. And then let's say I have a 9234 in slot 2. And let's say lastly, I've got a 9263 in slot 3. Okay, so I'm going to click Next. Notice it tells me what kind of module it is down here. So now it's going to create those modules, and it's going to give me a preview of what my project will look like. So notice I've got my CRIO target up here, I've got my chassis, I've got my FPGA target. If I expand it, notice that I've got module 1, 2, and 3 in my project. If I expand each one, I see that there's I/O for each of these modules. So I've checked it and things look good. I'm going to go ahead and click Finish now. So notice that by going through that wizard, I can also automatically generate a project that has all my different modules and my FPGA target as well. Okay, so this is just another way of creating a LabVIEW FPGA project. This could be a useful method if you're creating a project from scratch. However, if you have an existing project and you want to add an FPGA target to it, you'll have to do that manually by right-clicking on the project, like we showed you before. So just wanted to show you a couple different options. Now you can use the LabVIEW FPGA project template to create a LabVIEW FPGA project. Next, we will describe aspects of FPGA technology.